Okay, I'm Jim Frankenfield, and this is a short problem solution video for a physics problem. It's not really instructional. I just wanted to go through the solution rather than post it in written form. Thought the last part would deserve a little explanation. So the problem is that we have a boom holding up, like a boom on a crane, holding up a cable with a tension in it. Something's hanging from the cable down here by the T. And what we want to do is find the compression force on the beam. So we're used to a lot of problems that are really straightforward and everything's aligned in the X and Y direction, my I and J coordinates here. But in this case we need to find the force that's oriented along the beam. And there'll also be a perpendicular part creating a torque on the beam. And that's a little bit different. So let's have a look at this. So the first part, hopefully if you're doing this kind of problem, you know what to do with this. You just sum up the forces at A. It's a statics problem, nothing's moving. Sum of the forces equals MA equals 0. So in the X direction I have the boom force X component, and I have to the left a tension cosine 30, and I get the magnitude of my X component. And I sum up the forces in the Y direction, and I get the magnitude of the Y force, and when I put them in vector form with unit vectors, I get this. This is the force acting on the boom, minus I minus J. It's oriented down this way. So now it gets interesting because this is not at the same angle as the beam. And we have to find the components of this. In a sense, it's a little like friction problems on a ramp where you take your X and Y axis and tilt them along the beam. So the first part, the first way to do this is the easier way. And first we need the magnitude of the force, so we just find the magnitude of this vector, which I'm not going to go through, and that's just the square root of 3t. So what we have over here is the beam is at 45 degrees from vertical, so this is 45 degrees, and this resulting vector is at 30 degrees from the vertical. So I have 15 degrees between the force B, and the compression force. So if I want the component along the beam, this is 15 degrees between them, I can just take cosine of 15, that takes the component of this along this axis. So if I do that, I take the magnitude, which is square root of 3t, and I multiply it by cosine, and I get my compression force. So that's pretty straightforward. The torque would be the other component using the sine of 15, and I can find that. So there's a force acting in this direction, which is going to create a torque on the beam, and there is a force along the beam for compression. The second way to do this, which is what I think deserves a little explanation, is a little bit of basic linear algebra, which in basic physics we're often jumping ahead of the math that students have had, so some students may have this background and some may not. I have the force here on the boom, and I have to take the dot product of a unit vector in the direction of the boom. So I want the force in the minus 45 degree direction, and that's this vector here, minus I minus J. That's minus 1x minus 1y. It goes in the direction of the boom. But I need a unit vector, so I have to divide that by the square root of 2, which is the same as the square root of 2 over 2. So this quantity in the square is a unit vector. If I take my force vector and I take the dot product with this, I'll get the magnitude of the force in that direction. So the dot product is just the I part here times the I part here, so minus 1 times minus square root of 3 over 2, minus 1 times minus 3 over 2, and I add those up. I also had square root of 2 over 2, which is the same as 1 over the square root of 2. And I get 1.67 again. So in this case, I'm using some linear algebra and taking the projection. Dot product gives you a projection. So I'm taking the projection of this vector in this direction. And likewise, I can do that for the torque component. So that's a plus I minus j. That's plus 1 minus 1y. So that's aimed down this way, perpendicular to the beam. N is usually a normal. Here it actually is a normal vector. Here I didn't know what else to use, so I called it N parallel. This is N perpendicular. And I take the dot product the same way. This times this, plus this times this, and I have a square root of 2 over 2 again. And I get something very close to my previous answer. There's some rounding or something in there as a difference, which I'm not going to investigate. I just wanted to explain the methodology here. So it's a little bit different than having everything line up nicely in x and y direction. We actually have to first find the x and y components up here, but then we have to actually project that force along the beam and perpendicular to the beam, or boom. That means that the support down here at the base is not only providing x and y forces, it also has to resist a torque. So in the engineering implementation, that will need to be considered also. So that's kind of a nice short problem, and that's it. That's the end of the problem. I'm going to put this down here in case you want to freeze the video and check that out again. And that's it.